So we have been discussing about this different types of MAVs, and we have been discussing about this fixed wing type, then rotary wing type, flapping wing type, etc. in detail. So whenever we are considering or whenever we are designing such kind of systems, of course there is a need to investigate or need to design the kinematic and dynamics of the systems. So when we try to talk about the kinematic and dynamic, so of course people who have studied robotics, core robotics, they will understand like kinematics and dynamics of investigations or kinematic and dynamic derivations of these systems is slightly complex, and it gets changed with reference to the type of linkage of what we are using. Here in this particular case, like we are talking about a kind of an MAV, so appropriately, so we may need to deploy a kind of a dynamic equations, or we may need to deploy a concerned parameter catering towards these dynamic equations. So considering these dynamic equations, so let us consider this as a plane, and the movement of the this fly is from the center of the mass, which is along the plane. So ideally in this case, so we consider a kind of an initial frame, the final frame, and the kind of a vehicle frame which exhibits over here. And there are 2 points which is located on rigid body dynamics. One is OI and another one is a CM. So these SY CM is with reference to R cube is the vector that joins the extreme border OI with the rigid body center of the mass. So V and omega are the translation and the angular velocities respectively at any point R cube. F and tau are the forces at any point R cube. So when we try to look into the kinematic transformation equation from a dragonflyer body, it is given by this particular format, particular derivations, where this V dot corresponds to the kinematic transformation of the equation of these kind of dragonflyer body, which this is a kind of a dragonflyer body. Okay. So in this particular case, when we try to look into the key parameters, the key parameters includes the J, which is the total inertia of the vehicle, which is due to the rotor, and the electronics with the total mass mt, and U is considered to be the identity operator which persists. So when we try to look into the dynamic equation of the motion, so the total inertia is represented by JCMT, which is calculated according to this particular equation, where it depends upon the rectangular mass M2, M and Rm contributes to it, and the radius of the secondary element. And when there is a spherical shaped dragonflyer is there, M1 and R are the mass and the radius respectively for the main electronics. A and B are the length of the rectangular shape for the secondary electronics, which exhibits over here. Now, when we try to look into the kind of flapping wing arrangement perspective point of view, so in the case of a flapping wing, these flapping wing micro aerial vehicles are a class of an unmanned aerial vehicle that mimic the flight characteristics of a bird, a bat, and an insect. So they offer a kind of an unique advantage over a traditional fixed wing and a rotary wing MAVs, which is including a kind of an enhanced maneuverability, and it also has a kind of a concealment and effectiveness in the low Reynolds number environment. So when we try to look into the performance perspective point of view, so thrust is primarily generated by a wing deformation during flapping, while lift is similar to a fixed wing aircraft, but with additional contribution from unsteady aerodynamic effect, the optimal flapping frequency and significantly impact the performance. Whereas when we try to talk about the high frequencies, these high frequencies may decrease the thrust, so it may find a kind of an optimal balance is crucial. So in this particular case, we have two different strokes. One is called as an upstroke and the other one is called as a downstroke. So in this downstroke, we have a pronation in place, and then when we try to consider an upstroke, we have a supination in place. So in the case of a supination, so we have a kind of a orientation or a vector matrix which exhibits, and in the case of a downstroke, we have a kind of a pronation which exhibits. Now when we consider this flapping wing MAVs, so there are these flapping wing MAVs are ideally governed by a certain amount of physical principles. So some of the physical principles like Newton's law of linear motion, and it also depends upon the rate of change of linear momentum. So basically when we try to consider the rate of change of linear moment, so automatically, so we may need to equate it with reference to applied forces. So in the case of an applied force, we have the gravitational force and the aerodynamic force which is participating. So as far as in this applied force is concerned, so it is governed by the equation with the this is the overall coordination for a gravitational force, which is represented as G is the acceleration due to gravity, and FDS is the kind of an elemental surface force which exists. Similarly, when we try to talk about the Euler's law of angular motion, so in the case of an Euler's law of R dash is the position vector of small element mass with volume V, and rho A is the kind of a density which exists, and G is a kind of an acceleration due to gravity which exhibits over here. Now, when we try to look into the kind of a flapping wing MAs, so we have a wing and a body velocity. So considering only one side, the velocity of the right wing root in a body frame with reference to the inertial frame, VR wing is given by VR wing is U bar plus A RR. So RR is the portion of the wing root from the main body center. U is the linear velocity, and FW MAV is the kind of a flapping wing MAVs, and alpha is the angular velocity here. So here in this particular case, we have two sets of this one. So one is with reference to the linear velocities, and the other one is with reference to angular velocities. So with the reference to linear velocity perspective point of view, we have the U, V and W are the components of the linear velocities, which is focusing towards the X, Y and Z direction respectively. And in the case of this particular process, we have the PQR are the component of the angular velocities, which is represented in the XYZ direction respectively. Now, when we try to look into this flapping wing MAs, the wing and the body velocities, so the motion of the wing is with reference to the MAV, thus the velocities are represented as VSR wing, which are calculated with reference to the stroke plane frame as VSR wing S TSRB plus U plus alpha RR. So the angular velocity AR wing is given by AR wing is TBSR alpha plus W wing. So R wing is the position vector of the wing element from the wing root. RR is the position of wing root from the main body center, and U is the kind of a linear velocity with reference to flapping wing MAVs, and alpha is the kind of an angular velocity of the flapping wing MAVs. So when we try to look into this TBSR, so the TBSR is a kind of a rotational matrix which exhibits, and omega is the kind of a R wing which exhibits over here. So when we try to observe a kind of a flapping wing MAs, so these wing and body velocities are concerned. So we have two sets of characteristics. One is called as TBR and another one is T theta R, and the third one is called as a T tau R. So TBSR is TBR, T theta R and TRR. So where beta R is a kind of a deviation angle and theta R is a kind of a pitching angle, and these flapping angles are kind of a tau R. Now, when we closely observe this deviation angle, so these deviation angles are calculated with respect to YR stroke and YL stroke, and then there is a Z stroke is there. So this Z stroke moves up and down, and appropriately we get a kind of a deviation angle which is nothing but a beta R. And then similarly, when we try to consider a kind of an insert kind of arrangement, so in this insert, so we have a wing and then an X body and an XR stroke and an Z body which is available and a Z stroke. So in this particular case, this as far as these pitching angles are concerned, so this is going to be a theta R, and this theta R and theta SR can be considered. So like with reference to theta and theta SR, so appropriately you can find the deviation. And then when we have a flapping angle, so there is going to be a tau R. So in this tau R we have a towel and the left wing and the tau R and the right wing. So this tau R and the towel left wing and right wing, so we have the YL stroke which exhibits, and then the YR stroke exhibits. So this YL stroke will move in an appropriate direction and YR stroke will move in an appropriate direction. So we have the X stroke y stroke and z stroke are the strokes of the wing with respect to x, y and z of the MAV, basically these flapping wing systems. So as far as these flapping wing MAVs are concerned, so there is going to be a kind of an aerodynamic forces and the moments. The forces and the moments are developed on the body due to the motion of the wing. So the elliptical right wing in the right wing frame with XR wing and YR wing as x-axis and y-axis respectively. So let us consider R max. So let us consider R max be the total length of the wing, while chord max be the maximum chord length. So considering a small elemental step dr at a length rst from the wing root, so dl and dd are the differential lift and drag force acting on the element dr. So here dr is a kind of a chord which exists, and then when we try to look into it, so we have an XR wing and a YR wing, and then there is going to be a chord max which exists, and then we have the CR and the R max which exhibits over here. Now when we try to look into the sectional forces of this right wing, so there is a kind of a wing section which exists, and then there is a ZR wing, and then we have a U real which is almost like at a right angle of DL, and then there is an XR wing which pursues over here. So based on the frame with respect to XR wing and YR wing, so appropriately the axes are being assigned, and then like when we try to look into the R max perspective point of view, so these R max are considered to be the total length of the wing, while chord max be the like the overall maximum chord length, where a kind of a strip is considered. Now when we try to look into the overall aerodynamic forces and moments, so the chord length of the wing is given as CR, which is nothing but chord max, which is a root of 1 minus 4 RST by R max minus 1 by 2 the whole the square root. So considering the section of right wing in XR wing and ZR wing plane, so the relative velocity of R acting at the right wing element U real is root of U squared R wing plus W squared R wing. So U R wing and W R wing are velocity component in X and Z directions respectively. The inflow angle phi R is represented as phi R is equals tan inverse of W R wing by U R wing. Now the total length of this of an attack, which we call it as alpha R, which is acting on the right wing, is alpha R plus theta R by phi R. So theta R is the pitching angle and phi R is the inflow angle which exhibits. Now like considering the overall aspects, so we are addressing the angle of attack, so we are addressing the pitching angle, so we are addressing the inflow, we are also addressing the relative velocity of R acting at the right wing element, and we are also addressing the kind of aerodynamics force on the moment. Now like when we try to look into this flapping wing as far as this aerodynamic forces and moment, so we have a lift DL and drag DD on the section. So as far as this DL is concerned, so it is half rho U squared REL CL alpha R CR DR. So CL and CD are the coefficient of lift and drag respectively, and rho is the density. When we try to look into the URL is the relative velocity of air acting on the right wing element, and alpha R is the total angle of attack, and CR is the width of the differential element of the wing. Then when we try to look into the DD perspective point of view, so DD is a kind of a section which exhibits where we have a kind of half rho U squared REL and CD alpha R and CR DR which exhibits over here. So we have been discussing about this different forces which are evolved in it and the moments which are being evolved in it with reference to the overall flapping wing force and the overall right wing forces, etc. So we have discussed about the aerodynamic forces and its movements, and then we have also discussed about the lift and the drag overall calculations with reference to Ziga, and the force acting on the wing element with DFR wing and the moment acting on the wing element, and DL and DR are the different lift and drag force acting on the differential element of right wing, and phi R is the inflow angle, and R wing is the position vector of the wing element. So these differential forces and moments are integrated along the length to get the overall aerodynamic forces and moments on the right wing. So overall, like we have got a clarity about the different types of micro aerial robots as well as micro assembly of micro aerial robots, and what are the different factors which are being deployed, which takes care of the overall requirements, or like which takes care of the overall design of this system. Now we will discuss about this multi-robot system. So as far as these multi-robot systems are concerned, so ideally in this multi-robot system, we have a multiple robot which tries to interact with each other, and they collaboratively perform tasks. In fact, now there is also a buzzword on cobotics. Almost it's a kind of a it's a kind of a similar system which exhibits on a micro level. So as far as these multi-robot systems are concerned, these multi-robot systems refer to a group of robots working collaboratively to perform tasks at micro and nano scales. So these systems are distinguished by their capacity to communicate information. It is also meant for coordinating the activities, and it also useful for collaborative functions, and it also take care of executing a difficult task. So these systems are particularly useful for biomedical applications, especially for microassembly, swarm intelligence studies, and the targeted drug delivery. So ideally, wherever we need to have a particular portion, so appropriately we can just reach a particular task and we can disperse the delivery. So like in the case of this multi-robot system, like when we try to look into the functionality of this multi-robot system. So these multi-robot system should be a robust system, so that it has high enough, because it even though it is on a micron level, it has wide varieties of load which tries to act on it. So appropriately the system should be robust, and then there should be a kind of a distributed action which should exist on the system, so that these distributed actions are capable enough in such a way that it can have a kind of a it should have a flexibility to interact and appropriately create a kind of motion. Third is with reference to fast execution of tasks, like it should have a capability to have a high processing speed, so that it can interact in a higher form, and then it also should have a large range of tasks, like it should have a capability to cater the different tasks, including the flow of the system, interacting with the system, talking to each other, and finally creating a kind of an environment in a bigger area. So one of the important aspect is, with reference to this system, is a kind of a bigger coverage. So as far as this bigger coverage is concerned, it's a kind of a interacting more into this, like kind of a wider network, appropriately coordinating with the wider network. So as far as in this multi-robot systems are concerned, so we have a kind of two different systems which exist, like principles. When we try to look into the principles of multi-robot system, so we have a swarm intelligence. So the swarm intelligence basically refers to the ability of multiple simple agents to work together in a coordinated way. So it is inspired by a kind of a biological system like ant colonies, fish schools, and bird flocks. And the key swarm behavior includes like self-organization. These micro robots dynamically organize without any central control. Second most important aspect is with reference to this emergent behavior. It has a collective intelligence which arises from the local interaction. So as far as in this local interaction is concerned, like it tries to behave in an appropriate way. Then with respect to scalability perspective point of view, the system functions well regardless of the number of micro robots. So like it can maintain a particular scale, and appropriately it can be oriented. Now when we try to look into the communication mechanism, as far as these communication mechanisms are concerned, so micro robot in an MRS it can communicate in a better way, and it has a good physical interaction, like this robot bumps into each other, forming kind of a temporary structure. And as far as chemical signaling perspective point of view, similar to ant trials, these robots can modify their environment to leave the information for others. So it's a kind of like even in the case of ant also, you might have observed, so they try to create a kind of a droplet, and the next ant which is coming will start following this particular ant. So in a similar fashion, so a kind of a chemical signaling can also be deployed.
Next, one of the important communication is with respect to electromagnetic or optical signaling. So as far as these electromagnetic or optical signaling is concerned, it is used in a kind of an external control method so that it can interact appropriately. Okay, so these are some of the key functionalities or characteristics with reference to multi-robot system, with reference to SWAM intelligence and communication to SWAM. Now, if you closely observe in this multi-robot system, we have a decentralized versus centralized control. So as far as the centralized control is concerned, a central unit computes and assigns tasks to each micro robots. With reference to positive aspect perspective point of view, it has a high precision, it has a well coordinated movement. However, with reference to a negative perspective point of view, it's a single point failure risk and it has a communication overhead. With reference to decentralization perspective point of view, each micro robots make a local decision based on the environmental cues. As far as pros perspective point of view, it has a robust, adaptive and a scalable. And with respect to negative perspective point of view, that is with respect to disadvantage perspective point of view, it is highly difficult to achieve such kind of complex task without any direct coordination. So in the case of a decentralized system and a centralized system, appropriately based on the application, we can develop a system for a micro robot. And the case of a decentralized system, we appropriately apply a kind of a local decision for this particular system. Now, if you try to look into the overall coordination of it, this overall coordination of this multi-robot, so there is going to be a central system in place, and this central system is composed of several central control units and several agents. These agents SWAM can accept the unified scheduling of the central control unit and it complete their respective subtasks. And finally, it cooperates with complete and an agreeable main task. So each of their agent members can achieve these subtasks such as positioning, tracking as well as visual signaling. So now in this particular case is concerned, this CCU is considered to be the centralized system, and then we have a kind of a multiple system which has a kind of an agent members. So through this centralized system, appropriately the coordination happens along the agent members, and then there will be a kind of a continuous motion which persists over here. So this is a kind of a centralized system. This is the kind of a overall configuration of a centralized system. Similarly, when we try to talk about a decentralized system, as far as coordination of this multi-robot, a decentralized approach, it basically eliminates the dependency on a central controller and it enhances the system resilience and the flexibility. So as far as this computational task is concerned, these computational task is performed by any or one or more robots in team. So ideally what happens is this as far as in this particular computational task, like one main center coordinating multi-robot will perform the task and it will try to deliver the appropriate specific configurations to the multiple system. So as far as in this particular case is concerned, there are no specific leaders throughout the mission and it allows all the other robots to proceed with their computation even if one of the robot fails. So that is one advantage of this decentralized system. Now, there is a different configuration which exists, which we call it as a distributed system. So as far as this distributed system is concerned, so these distributed control system also play an essential role with reference to SWAM robots. So this distributed system is a kind of a multi-level computer system with communication network as the link, and it composed of a process control and a monitoring. So as far as in this system is concerned, we have a target, then there are robots in place, and then there is an average position in place. So it is integrated with the computer and communication, and it is meant for displaying and control the technology. So as far as in this particular case is concerned, it's so one of the key idea of this decentralized control system is it has a kind of a centralized operation with a kind of an hierarchical management. So for example, so since you have a kind of a centralized portion over here, this centralized portion will decide about the influence of the robot or the participation of the robot towards a particular operation or the particular management. So this system has a capability towards like kind of a flexible interaction or a kind of a flexible transformation or a flexible configuration based on the convenient configuration. So as far as in this particular case is concerned, the distributed control system has a relative advantage and it has a kind of a distress factoring with reference to this multi-robot system compared to the centralized system. So ideally this has a kind of a better advantages, like wherever, like for example you have a multiple micro robots, either it is in the form of a swan based, like either we can have a aerial vehicle or like we can also have a kind of a caterpillar kind of arrangement. This communication between the caterpillar arrangement and the aerial vehicle can happen appropriately, so that it can be helpful for us to emphasize a particular configuration. Okay, so this is one of the key aspects which is to be considered with reference to this multi-robot system. So overall, if you try to look into the picture, so we have the robotic systems in place and then their average position at the targeted, and then appropriate calculations are maintained in such a way that there is a kind of an optimum movement which exists. So overall in this module we had discussed about the different microassembly, the microassembly performances. We had also discussed about this micro aerial vehicle, few so we had discussed about the different parameters which are involved with reference to design of this micro aerial vehicles, about the overall links and the mechanisms, etc. And then we had also discussed about the different types of multi-robot system, how these multi-robot systems are deployed for different applications. Okay, so these are some of the reference which we have used for preparing this particular aspects or the particular topics related to these microassembly for micro robot. So the next module will be focusing upon the biomimicry.